All right, welcome to today's notes of gazelles out of cannon. So we're going to do this. It's going to kind of bring us all back together, talk about projectile motion, specifically with projectile motion at angles, and then this should give you enough information to be able to carry on with the rest of your projectiles tic-tac-toe. So you have the notes in front of you. It's projectiles launched at angles, aka gazelles out of cannons. So yeah, we're going to be shooting gazelles. We kind of put gazelles into some precarious situations in this class, going off of cliffs and then now out of cannons. So we're going to draw a picture. The sample problem says a gazelle is fired at 80 meters per second from a cannon inclined at an angle of 40 degrees above the horizontal. How long does the gazelle spin in the air? How far away does the gazelle land? And what is the maximum height that the gazelle reached? So the first thing we want to do is to draw a picture. So here is the cannon. Here is my gazelle. Don't laugh at my gazelle. And it is going to be going in a projectile path, a parabolic path, until it finally lands on the ground someplace over here. We're basically going to say that it originates from the back of the cannon and goes to a point over there. So, what are some things that we know? Well, we definitely know that the velocity is off at an angle, and it is 80 meters per second. But the problem is that we want to really put it into an x and y table. So is it the x or is it the y? Well, this is neither, but it's both at the same time. So I'm going to try to color code some things. So we will use, in the x direction, we will use red. Okay, red. So here we go. We have a portion of this velocity that we will call the initial velocity in the x direction. And then we also have a portion, let's see, what am I going to do? Let's do blue. We have a portion of that velocity that is in the y direction, so that would be the initial velocity in the y. And then, of course, we have our angle of 40 degrees. So if we know the hypotenuse, how can we figure out one of the sides of the triangle? Well, if we know the angle, that means we can still use a trig function. So if we want to go and do the vertical, we know that this is the opposite side, right? It's the opposite side. So if we know opposite and we know hypotenuse, then we can use sine. So sine of the angle, sine of 40 degrees, would equal the initial velocity in the y direction over 80 meters per second. Or that the initial velocity in the y direction equals 80 times the sine of 40 degrees. Okay? And if you do that in your calculator, you would get 51.4 meters per second. Similarly, if we are going to do the x direction, we can do cosine, right? Cosine of 40 degrees would be equal to VO in the x direction over 80, or that VOX would be equal to 80 cosine of 40 degrees, or 61.3 meters per second. So now, is the 80 in the x or the y? Well, it's neither, but we have an x direction of 61.3 meters per second, and we also have a y direction velocity of 51.4 meters per second. So we are now ready to set our lovely, whatchamajoohickey, the t-table. So we have x, we have y. Let me get this t-table set up. There we go. Let's get back over to colors. So we use red for x, right? So the initial velocity in the x direction was 61.3 meters per second. Do we know anything else in the x direction? Well, sure we do. We know that the acceleration in the x direction is 0. Right? 0 meters per second. All right. What about in the y direction? Do we know anything? Well, we just calculated the initial velocity in the y direction, and that is the 51.4 meters per second. We also know the acceleration in the y direction is 9.8 meters per second, but now we have to be careful. The initial velocity in the y direction, if we come back over here, that's pointed upward. Right? It's pointed in the upward direction. But what about acceleration? Acceleration is pointed in the downward direction. So that means these have to have opposite signs. So we have a negative 9.8 with a positive 51.4. So that's showing us mathematically that they are in opposite directions. So that's pretty much the only things that we know. Well, kind of. We know a few other things that we can make use of. Specifically, one of the things that's going to make our life easy is right here at this landing point, right here at the very end. We are interested in what the time is, sure, but we actually know what the delta y is. What is delta y here at the very, very end? Well, if we're measuring off the ground, our y direction, we go up, we come back down, but we'd still end up on the same level that we started, so delta y is actually equal to 0. So at that particular location, delta y is equal to 0. That helps us out with the first question. The first question, which was time. How long is the object in the air? So since we know a little bit more in the y direction than what we do in the x direction, that's supposed to be a question mark. There we go. Question mark. Nah, anyway. So we can use our favorite equation, our projectile motion equation. Delta y is equal to VOYT plus 1/2 a in the y direction times t squared. So it's just that big old lovely equation that's usually written with x's, but this time it's written with y's because we were talking about the vertical direction. So we have 0 is equal to 51.4 meters per second times time plus 1/2 multiplied by negative 9.8 meters per second multiplied by time squared. So how do we solve that? Well, one of the best ways to do it is by factoring. So we have this equal to 0, and everything on this right side has got a t in there. So we have 0 is equal to, and I'm going to drop my units just so we don't get confused, 51.4 plus, actually, we're going to do minus 4.9 t times t. So where'd the 4.9 come from? Well, that's 1/2 a negative 9.8 and gives you a minus 4.9 right there. So this, if you remember this from math class, there's two eventualities here. One where t is equal to 0, okay? So what does that say? Well, that says that y is equal to 0, delta y is equal to 0 when t equals 0. If I come back over here, well, t equals 0 over here. Well, of course delta y is equal to 0 at the very beginning. We haven't launched it yet, all right? So then we come back and we say, well, there's another situation where this in the parentheses could be equal to 0. So if 51.4 minus 4.9t is equal to 0, then that would be equal to when t is 51.4 over 4.9. Okay, I'll let you do that algebra. And that's moving the negative 4.9 to the other side with the t and then dividing it back over to get t by itself. So we would get 10.5 seconds. So how long is the Gazelle in the air? Well, it takes 10.5 seconds to go all the way up to the top and come back down. So if we go back to our diagram, our time is 10.5 seconds all the way here at the end. Well, how far away does it land? Well, that's easy now that we have the time, because if we take a look back at our equations here, we know time is, or our givens, our time is 10.5 seconds, which is now available for both sides, because its time is not directional. So we have all this stuff in the x direction, and enough to be able to figure this out. So if we want to know our delta x, let me switch back over to red. So delta x would be the same equation, VOXT plus 1/2 AX t squared, but this part is going to go away because we have no acceleration in the x direction. There's no sideways gravity. So delta x is equal to our VOX, which would be 61.3. Wow, cursive numbers don't really make sense. 61.3 meters per second multiplied by our time, 10.5 seconds. And so our delta x would be equal to 643.7. So that's how far away the Gazelle would land. A little bit more than half a kilometer. All right, let's talk about our last one. So our last one is, how high does the Gazelle go? No, that's not what I want. How high does the Gazelle go? So if we're going back over here, I'm going to switch back over to my blue. We want to know, how far up does he go? What is the delta y at this location, the highest point that it gets? Well, what do we know about that location? We know actually quite a bit of stuff about this location. We know if we just throw something straight up in the air, the y velocity is going to decrease until it gets all the way up to the very top, and then it's going to stop. So our velocity in the y direction up at the top is 0. And if you notice, this nice parabolic curve here is very symmetrical. So if it takes 10.5 seconds to get all the way to the end, so that means that at the midpoint, it would take 5.25 seconds. So we know an initial velocity in the y direction. That's this guy down here. We know a final velocity in the y direction at the very top. We know a time it took to get there. And that's enough information for us to figure out what delta y is. One of the ways that we could do that, highest point delta y, would be using the average velocity formula, the 1/2 times Vy plus Voy times t. That's not the only one we could use. We could definitely use any of the other ones. But since we know what the final velocity is, we can figure this out. So that's going to be 0 at the very top. So delta y then would be equal to 1/2 multiplied by the initial velocity of 51.4 meters per second multiplied by the time of 5.25 seconds. Remember that 5.25 seconds is the amount of time it took to get only all the way up to the top. Not the entire thing, but halfway through the entire thing. So delta y is equal to 134.9 meters. I probably would round that to 135. Okay, so we have finished all of that stuff. We can move on to the next problem. So, similar scenario. We have our cannon here. There's our cannon shooting the Gazelle out the way. So, the problem in this case is that we are sticking a 40-meter tall fence at a distance of 50 meters away. Okay, that says 50, I promise. 50 meters away. So the question is not how far does he go or how long does he stay in the air, but pretty much the question is, will he hit the fence? Will he just miss it? Is it going to be one of those cases where he hits it? We don't know. So what we need to do figure out is how high is the Gazelle's path when it gets to the point where it is 50 meters away from where he's launched. So we're going to do our same XY stuff, and we can actually borrow some values from the previous problem. The previous problem is allowing us to do that. So we know our delta x is going to be 50 meters in this case. Our VOX is going to be the exact same, 61.3. Why is it the same? Well, it's the same angle, it's the same initial velocity, so we don't have to recalculate those vectors. We still know the acceleration in the x direction is 0 meters per second per second. We can take a look at the y now. So the y has an initial velocity of 51.4 meters per second, has an acceleration of a negative 9.8 meters per second. And that's all we know, because we don't know delta y. We're trying to figure that out. So with our projectile stuff, we always like to find time first. If we can find time first, then that makes our life so much easier. So in this case, which do we know more about? We know more about the x direction to find time. So let's do that. Our equation that we know and love, delta x, is equal to VOX times t plus 1/2 a in the x direction times t squared. That goes away because the acceleration is 0. So now we're going to find time. So in this case, time is delta x over the initial velocity in the x direction. That's the algebra there. So our delta x is 50 meters. Our VOX is 61.3 meters per second. So our time ends up being 0.82 seconds. 0.82 seconds. I can do that better, I promise. 0.82 seconds. Well, it's better. Still not great. All right, so how do we use the time to figure out where the Gazelle is? Well, if we want to know where the Gazelle is at that time, because remember that time he is exactly 50 meters horizontally away from the cannon. So at that time, then we can plug it into the exact same equation, but in the y direction, delta y, and that's the wrong color. So we are going to go to blue. Here we go. Delta y is equal to VOY times t plus 1/2 at squared. So we want to know what delta y is, so this is already solved for us, so we can just start plugging in information is. Delta y, the initial velocity in the y direction, 51.4 meters per second, meters per second, multiplied by our time of 0.82 seconds, because that's the time that he would be at the fence line, plus 1/2 times a negative 9.8 meters per second, multiplied by 0.82 seconds squared. And what we get out of all this is 38.9 meters. So what happens? Does he hit the fence? Well, yeah, the fence is 40 meters tall, so he's going to clip this to the top of the fence. By how much? By, 1.1 meters he will hit the fence. He hits the fence. So this particular problem actually has a pretty direct bearing on one of the choices that you have in the Projectiles Tic-Tac-Toe, which is that AP Physics B free response question. It's very, very similar to this. All right, so what's left in your packet are some more problems for you to try. So there's only 4 there. I'm going to turn onto the back side of that packet, but you have a nice blank page. We're going to do one last thing. So if you're planning on trying to do the practical, then we're going to help you out with that a little bit. So let's start off with the practical. So here's the table. Here's the marble launcher off the table. So the marble is going to be launched. It's going to go pew. Yeah, you like my sound effects? I know you do. And we want to know, where do we put the cup in order to get that marble to land in the cup? Okay? So some things that you are allowed to measure. You are allowed to measure the height at which the marble is released. Notice how when I drew that in there, it's not the height of the table, although the height of the table is included in there, but the marble launcher is going to be released from a little bit above that. So there's the delta y, so you can measure that. I'm going to throw out a number. I'm going to call it 1.2 meters. I don't think that's exactly what it is, and depending on the tables and depending on which room you're in, it could be 1.2, it might not be 1.2. Okay, so we have an issue though. What if the marble decided to, not decided, but you calculated it to hit exactly right there, but we used a cup that was a little bit skinnier and we hit the side of it? Okay, would that give you bonus points? No, because it doesn't land in the cup. So we probably want to know what the height of the cup is. That way we can take this into account, making sure that it actually goes into the cup. If we can calculate that it's going to be right there, then we can be pretty sure that it's going to go in the cup. So I'm going to call that 12 centimeters. So the cup height is 12 centimeters. Now, another thing that you're going to measure is the velocity of the marble as it comes out. You'll use your photo gates, right, to measure the velocity. So I'm going to say, for example, we are going to have a velocity of 3.2 meters per second, 3.2 meters per second, which means that we have a y part of that, velocity in the y direction. And I'm going to let you figure out what that is, or at least how to get it. I'm going to tell you what it is. It's 2.45 meters per second. Okay, it's up to you to figure out how I got that number. And here, this is a velocity in the x direction. These are both initial quantities. And this is going to be 2.06 meters per second. So again, it's up to you to figure out how I got that value. So let's get some stuff going in the x and y tables here. So in the x direction, what do we know? Well, like always, we know the acceleration is equal to 0. Our initial velocity in the x direction is the 2.06 meters per second. And we're looking for a delta x. We don't know. In the y direction, we want an initial velocity in the y direction to be 2.45 meters per second. We know the acceleration is a negative 9.8 meters per second. And we know the delta y would be 1.2 meters, but subtracting off the height of the cup of 0.12 meters, and that would be 1.08 meters. So why do we do this? Well, again, we want to make sure that we don't hit the side of the cup. So if we can calculate where the marble is when it gets to the top of the top of the cup, and we put the cup so that the opening is dead center with that, then we are pretty confident that the marble will actually go inside the cup. If it hits the back of the cup and knocks over, it's fine. It's still within the cup. You still get the bonus points. But we have one more thing to add on to this, though. The actual value of 1.08 meters, that's the displacement. It's a displacement going in the downward direction. Well, if we're calling negative 9.8 negative, then we have to call this as a negative 1.08 as well. So our displacement is going down. So, again, we want to find time. And this is going to be a little bit more difficult. So if we say delta y is equal to VOY times t plus 1/2 a in the y direction t squared, then we would have negative 1.08 is equal to 2.45 times t minus 4.9 t squared. Okay, that 4.9, remember, came from 1/2 of 9.8, and it's a negative. So how do we solve that? It's not as easy when we have nothing that's not a 0 over there, right? So if you plot this function, actually we can't plot it in the way that it is. If we say 0 is equal to, I'm going to rearrange this a little bit, negative 4.9 t squared plus 2.45 t plus 1.08. If you plot that function, y versus time, it would start up here at 1.08, that's the initial position, go up, then come back down. All right? Now this is a y versus time graph, y position versus time. This looks like exactly what the marble actually does, right? It goes up and it comes back down as it's going forward. But we have to understand that this is a graph versus time. So this is not describing the actual trajectory of the orb, but it is talking to us about that fact that it does go up and then it comes back down. And if we could figure out what the 0 point is here, where the root of this function is, then that would be our time that we're looking at, the time that it takes to get to the height of the cup. So there's two ways that you can do this. You can put this equation into a calculator and have it solve for your 0, okay, and that's completely fine using a graphing calculator. You would get that the time is 0.78 seconds. Okay. The other way, the harder way, is to actually use the quadratic formula, using t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, where this is your a, this is your b, and this is your c. But you would find that you get the exact same thing. And you would get two roots. One of them would end up becoming negative, and that's this root back here, which doesn't mean anything for us. It's negative time. So that is the time it takes to get to the top of the cup. So there we go. We have our time. So how do we figure out a delta x? Well, delta x is just going back to our normal equation. Delta x is equal to VOX times t plus 1/2 a in the x direction times t squared. But that goes away because it's 0. So our delta x then would be our initial velocity in the x direction, which I don't remember. I'm going to go back to my table and say, oh, it's 2.06 meters multiplied by a time of 0.78 seconds. And we would get a delta x of, drum roll please, 1.61 meters. So if you put the cup 1.61 meters away from the marble launcher, then you would have a good chance of it just landing right inside the cup. All right, so with these three examples, you should have enough information to get all of your rest of the projectiles tic-tac-toe finished over the next couple of days. You have the rest of the class period to work on your projectile stuff, and if you are wanting to do a practical, then you will need to do it in front of an actual teacher, not the substitute. So if you're wanting to do a practical, you can be thinking about it, but you're not allowed to do it unless one of us is present. So be looking at what else you could do at this point in time. You can get a Chromebook or a laptop and work for the rest of the period. All right, good luck.